Okay, so welcome everyone to the second lecture of the Loop Quantum Gravity series of the Basics of Quantum Gravity School. The school is organized by the International Society of Quantum Gravity, and the LQG lectures are given by Haggard. And today's topic is gravity as a gauge theory. Hal will take a break in the between the lecture, then we can collect questions, and you can also ask questions at the end of the lecture. So yeah, with this, thank you, Hal, again for participating in the school, and please go ahead.
Thank you, Johanna. Welcome, everyone. Delighted to be with you here again. So as Johanna mentioned, I'm going to be talking about how we formulate gravity as a gauge theory today. With respect to the first lecture, it's significantly more technical, but I also want to try to build up to that technicality. So I'm going to start at the beginning and try and tell you a little bit about what a gauge theory is. All right. So first of all, a couple of questions going back to the last discussion from a week ago. I'll ask you to think again, what do we mean by a force? What is a force? You don't have to respond in the chat, but I'll wait for a few seconds for you to think about what your answer to this question is. So I quite like this picture because for me it sort of illustrates the answer, which is that forces are forces of contact. So you can't really exert a force on another object unless you go and are in contact with that object and use that contact to exert the force. So I was emphasizing this in the context of gravity last time because of this second question, which is quite interesting. How is it then that some objects exert forces on one another without contact? And so this is my second question to you. It was the second thing we sort of began with last time. And again, I'll give you a second to think about your answer. Here I'm illustrating it with the electric field, but the same principle applies to the gravitational field. So the answer that we mentioned last time is that you have to start thinking of some physical things as being much, much richer than objects in the traditional sense. So the electric field is a field. It permeates space. And the contact is a contact between one part of the field with the neighboring part of the field with the neighboring part of the field. So, Faraday's electric field lines have become very physical in this sense. We take them seriously as the physical entity that spreads throughout space. And Einstein's space-time is the gravitational version of this, where it's locality in space-time that allows this contact. This contact. So how is it that the Earth exerts a force on the moon? Well, the Earth exerts the gravitational influence on the neighboring spacetime, and that neighboring spacetime exerts gravitational influence on the neighboring spacetime to it, and that extends all the way out to the moon. So these are the kind of important field concept that lays at the foundation of what I discussed last time and that we're going to do today. So as I did last time, I'm going to give you a sort of prologue, a beginning introduction to what we'll be discussing. And my prologue actually builds on Maxwell and his thinking about electromagnetism. So I love this quote. It's from an article by Karen Briard. It says, in 1870, Maxwell wrote in a letter to his wife that upon visiting his alma mater, Trinity College, he learned there was a legend that he used to toss cats from school windows to watch them.
May I interrupt you?
Please, please.
Have you, change the slide because we only see the first slide.
No. You don't see it changing at all?
Yeah.
Okay, yeah. Let me stop sharing and restart. Thank you for interrupting.
No worries.
Okay. Are we on the second slide now?
No. No, it's first.
And now?
No.
You have the chat open, Hal?
I probably do. Let me see if I can close it. All right, let's try again. I can also share my whole desktop if that's not going to work. What about now?
Beautiful.
The
Yeah.
second.
Yeah.
Okay.
Changed.
So sorry, because the pictures are the best part of these review questions. I'm so sorry. So
You can't go
here I
wrong
was,
with cats.
yeah, here I was showing you what a force is as a force of contact. So here's the cat pushing on an egg about to launch it off the table. So clearly that's the force of contact. And here's the force without contact. You can see the two balloons electromagnetically repulsing each other here, and the foam peanuts stuck to the cat. So this is quite remarkable to me that there are such forces, that you can have a force without contact. And it's this field concept that leads us to these ideas. So here's the Maxwell quote. This is a picture of Maxwell. He learned that there was a legend that he used to toss cats from school windows to watch them acrobatically land on their padded paws. And here I really wish I could do a Scottish accent for you, but I can't actually do it. I had to explain that the proper method was to let the cat drop on a table or bed from about 2 inches, and that even then the cat lights on her feet. So I love this quote because he's not denying that he dropped cats. He's just saying, I didn't do it from windows. There's a raised hand.
Once again, the slide is not changing.
Oh my
Sorry.
goodness.
Yep.
Every time you have to go back and then show the thing.
Or maybe you can export to PDF and
I can
maybe-
certainly export to PDF. I already did that. Let me try one other thing before we do that. I'll try to share my whole desktop instead of just Keynote. All right, can you see the quote from Maxwell now?
Sure, yes.
yeah, maybe you
Try to
can
change the slide
start
list.
changing, other slides. Yeah,
Yes.
yeah. Now we can.
Change
Yeah.
it. Perfect.
Okay. So Maxwell wasn't denying that he'd done these experiments on cats at all. He was just saying that you have to do it in a humane way. So I first encountered this this question of dropping cats in an old Scientific American article in 1980, and I just can't believe this picture. You see the scientist holding the cat by its forelegs upside down and the cat meowing, and it's quite clear the scientist is about to drop this cat. So all the way from 1897 to 1980 and to current day, people are dropping cats and asking what's going on. And I think a big question here is, why are they doing this? What is this about? And there's a beautiful experiment that was done in the late 1800s. So Maxwell and many other physicists of the time had thought a lot about this cat question of how does the cat land on its feet? And in fact, Mary was one of the first inventors of photographic techniques. And in fact, he took photographs of cats falling and was the first one to give a physical explanation of this. The paper was published in Nature in 1894, and here are some of the images from that paper. So you can see Mary holding the cat on the right part of the image, and then it slowly falls and flips over, and you see the cat land on its feet. I'm not sure why it reads right to left. I suspect somebody at some point flipped this image. But so this is a side view, and then you can also see a front view of the cat flipping over. And using this sort of stop motion photography, Mary was able to explain what it is the cat's doing in this process. But again, I want to ask the question, not so much how do we explain how the cat falls, but why were scientists so intrigued by this? And you all have good context for this. The puzzle is the following. If we do the experiment right, that is, we carefully release the cat from rest, then the cat has no initial angular momentum. But here, the cat is a free system. There's no external torques on it. There's just gravity acting at its center of mass and causing it to fall. And if there are no external torques, it doesn't gain any angular momentum in the fall. And so it becomes actually quite mysterious from a physics perspective how it is that the cat turns over without any angular momentum. How do you cause a rotation when you have no rotation? It seems like a contradiction in terms. And that's what got Maxwell and many physicists interested in this question. So I'm going to try and answer this question, but I'm not going to try and do so right away. I'm mostly going to use this question as a way to introduce you to gauge theory. And once we have built up the idea of a gauge theory, we can try and answer the question within that gauge theory. So the plan for today is to tell you about what falling cats as a gauge theory means. It's going to be a very simplified model of a cat. You may be a little disappointed. It's not a perfect model of a cat by any means, but it actually, for me, serves as the most concrete introduction to gauge theory that I know. Once we have that context, well, the canonical gauge theory for physicists is electromagnetism. So again, you can see how Maxwell was starting to think about these sorts of things. And so I'll build up a bit of technical machinery and discussion of electromagnetism as a gauge theory in the second part. And then finally, we'll go on and start to formulate general relativity as a gauge theory. Last class, I tried to motivate that framing GR as a gauge theory brings it closer to the other descriptions of fundamental forces that we know, and is hoped to make it bring it closer to the quantization process. Certainly within loop quantum gravity, this is a foundational move that we make in order to quantize the field. All right, so that's the plan for today. I made a little bit of false advertising last week. I thought I might get through the GR as a gauge theory completely today, but I'm only going to get halfway through, and it's actually nice. It splits nicely. So the other half of GR as a gauge theory we'll do in the next lecture, and that connects with this topic of spin networks, and so that's a nice split that we'll do. All right, so let's begin discussing cats as a gauge theory. So here is my very super sophisticated model of a cat. We're going to imagine two massless rods. So they're in dark gray here, each having the same length. We'll call it R. And they're massless, so they don't do anything, but they're hinged at the origin of our coordinates. At the end of each rod is a mass, and I've colored these two masses because I want to think of them as distinguishable. I want you to be able to recognize which one is which. So the red mass you could think of as the cat's tail or its back, and the green mass as its head, or something like that. That's my very rough model of the cat. And I'm going to pick some coordinates. I'll call them XS and YS. These are, the subscript S is to denote that these are spatial coordinates. So I'm thinking of it that way. But I'm also going to use angles a lot to describe the orientation of the cat. So theta is going to be my orientation coordinate. It's up from the spatial x-axis. And alpha is going to be my shape coordinate. It's going to describe how the cat is bent. So, you know, if the cat was to extend its paws out in front of it and its back paws out behind it, then alpha would get longer. If it was to contract in the way that cats do, you know, raising their back up, it would be alpha getting smaller. So this is the model of the cat. And in particular, to try to capture that aspect that we mentioned, that there are no external torques on the system, we're going to think of the pivot as being a kind of muscle. This is the cat's flexibility. But that muscle is an internal force. It exerts that force to change its shape, but it's not acting on the cat as a whole. It's acting internally. And that means that this muscle can never generate any external torque on our system. So this is also a 2D model of the cat. I'm not going to try and do the full 3-dimensional picture where it's a planar cat, if you like. So that's the setup. Just to make note of the fact that alpha is an angle and ranges over 0 to 2 pi. And one of the reasons I'm distinguishing the red and green masses is that I want not to get confused about whether I'm talking about alpha, or if I took this all the way down to 2 pi minus alpha, I don't want to be confused about which one is alpha and which one is 2 pi minus alpha. So by making these two masses distinguishable, it's easy to tell which one I'm talking about. Alpha always goes from the red mass to the green mass. So this shape coordinate, this internal coordinate that describes the shape of the cat, takes values in the circle. So this is not original to me. I wanted to say that right up front. This is in a very nice review paper in the Review of Modern Physics by Robert Littlejohn, who is my PhD advisor, and Matthias Reinsch. The paper is really concerned with the n-body problem, and the cat is just a warm-up for the n-body problem as a gauge theory. I recommend the paper, but here we're only going to talk about the cat part. All right. So today, unlike the introductory lectures, I've got exercises spread throughout. These are sort of an excuse, it's a school, you should do things, do calculations to learn what we're talking about, but also as a way for me to skip having to do some calculations in front of you that would be painful for you to watch me do. So using your favorite definition of angular momentum, R cross P or I omega, whatever you like to use, I'm asking you to go ahead and calculate the total angular momentum of our cat model. The way I've set things up, the cat's constrained to the XY plane, so the total angular momentum is just the Z component of angular momentum, if you think of adding in a third axis here. And it's a quick calculation, and you get this first line of the slide, first displayed line. But if you switch to the angular coordinates, the orientation and shape coordinates that I was mentioning, you'll find that this first term reduces to theta dot, and throughout today, the dot notation will always stand for the time derivative of the quantity. So the first term reduces to theta dot, and the second term turns out to reduce to theta dot plus alpha dot. And so when you add up the angular momentum contributions here, you get 2 theta dot plus alpha dot. You could and should complain, wait, what happened to the mass? What's going on here? I'm starting to set everything equal to 1. So we'll do that a lot today. It's a theorist trick to make calculations a little simpler. So yeah, I've basically gotten rid of R and M completely, just to focus on the coordinates description of what's going on. If you want units, take the M and R non-1, and you'll see units. Okay, but what's the point here? The point is to try to capture this feature that Maxwell had noticed, that the total angular momentum is 0. And if the total angular momentum is 0, then what we have is that 2 theta dot plus alpha dot must vanish. And a change of shape, that is, if the cat uses its internal muscle to change how its limbs are oriented with respect to each other, forces a change in orientation. So that's just because this is acting as a constraint on our system. Anytime you change the shape, well, that would change the angular momentum unless the orientation changed in exactly the right way to compensate the change in shape. So we start to see a glimpse of a theoretical explanation for the cat maneuver. The idea is the cat is internally changing its shape, and by doing those internal changes of shape, it's actually changing how it's oriented in space. Unfortunately, my simplified model of a cat is too simple, and we'll see why in just a second. But first, I want to make a sort of mathematical observation. So we had our total angular momentum here. And I want you to notice that once we set it equal to 0, well, we can clear all the time dependence and think of it actually as a relationship between differentials. So if I make a differential change in the shape of the cat, well, that results in a compensating differential change in its orientation. And this is going to be an important theme throughout today and part of our way of dealing with gauge theories, which is to work with these differential forms. Okay, so suppose that the cat changed its shape so that the green mass moved by a little change delta alpha over 2, and the red mass moved by a change delta alpha over 2. Well, we can plug that in and just to integrate this relationship. And we see that the total change in shape is delta alpha, and correspondingly, the total change in orientation is 1/2 delta alpha. And so this kind of results in something a little bit trivial. Yes, the orientation did change. It changed by exactly the amount that the red mass moved backwards. And so what ends up happening is that the bisector, the dashed line in this figure, is fixed throughout this whole process. So if we were wanting to model the cat's reorientation, if we wanted the cat to actually be able to land on its feet having been dropped upside down, that's going to require reorientation that completely flips everything upside down. And this model is just not going to be able to do that. It's constrained to always maintain this bisector. Maybe something else to mention, I'll go back to the picture so you can see this. You'll notice that the initial configuration, the initial shape of the cat is essentially legs fully extended. And the final configuration of the cat, well, is also essentially legs fully extended. The tail's in a slightly different position, but the tail's not very massive. So the tail can't be a huge part of the story. So very roughly speaking, the cat has the same shape at the beginning of the process and at the end of the process. So the reason I want to mention that is if we go back to our model, if you imagine that the cat did that thing, it changed shape from this initial slightly translucent configuration out to the darker one, but then changed shape back, well, that full deviation would bring it back to the same orientation. So that's one of the reasons that this angle deviation, this orientation isn't that interesting in this case. The bisector is preserved. That means when you come back to the same shape, nothing has happened orientationally. All right, so what's our conclusion? Before we get to our conclusion about this model, a little bit more terminology is useful for gauge theory. We don't have to use the space axes that I started out with. My space axes are in dark gray here, and something that we often do in gauge theories is adopt other coordinate choices. So in the context of this cat problem, you could imagine a set of body axes, like the red axes. So the red axes, we choose the x-axis to go through the red mass. But that also, we could do different things. We could choose the green axes, where the x-axis goes through the green mass. And the point is, you can do any of these things. And often it's useful to go from one to the other. And of course, when we go to the convention of the red body axes, then we have a different orientation coordinate. Let's see. Oh, I'm sorry. I'm going to describe the transition from the red body axes to the green body axes. That's the way I want to say it here. So the theta prime coordinate is going to go out to the green body axes, the theta to the red body axes. And you see that if we define things that way, then theta prime is just theta plus alpha. And which axes we use is purely conventional, and we call it a gauge. We call these gauge coordinates, and the relationships between them gauge transformations. But the main thing I want to say here, the interesting thing, which isn't just a convention, is that the shape of the cat, that is the angle from the red mass to the green mass, doesn't depend on our gauge choice. Doesn't depend on the coordinates we're making. So this is a really useful thing. Alpha is a gauge invariant. So that's an interesting thing, that there are both gauge invariants, like the shape of the cat, and things that are non-gauge invariant that we're still interested in, like the orientation of the cat. Of course, the cat really cares how it's oriented, right? It wants to land on its feet. Okay, so the conclusion of our simplified model of the cat was that we couldn't get the cat to land on its feet with just two masses. But we acknowledged from the outset that it was a way too simple version of modeling our cat. The cat can move its body, it can change its shape in a much richer way than what we modeled just there. So it turns out we don't have to go very far to already get something much more interesting. We just add in one more mass. So again, I use a massless rod of the same length just to make life easy. Again, I set the masses and the lengths equal to 1. But this time we have two shape coordinates. So our first shape coordinate is the angle that goes from the red mass to the green mass. Our second shape coordinate takes the axis determined by the green mass and keeps track of how far the blue mass is from that axis. And again, we constrain everything the same way. So there are muscles at the pivot O and at the green mass that allow the cat to change shape. So it can control its alpha and beta, but that's an internal change, doesn't change the angular momentum. So again, the total angular momentum must be 0. This is a bit of a harder calculation, a bit more interesting, but I've recorded the result for you here. If you calculate the total angular momentum of this, this less simplified model of a cat, you find this expression here, 4 plus 2 cos beta theta dot, 3 plus 2 cos beta alpha dot, and 1 plus cos beta beta dot. And here the significant thing is that the coefficients of each of these evolutions of angles now depend on the shape of the cat. So the coefficient of theta dot depends on beta, and similarly for the others. So we're going to do something quite general now. We're going to reorganize this equation just as we did before and solve for theta dot. In that solving process, of course, we'll get coefficients of the alpha dot and the beta dot, and we're going to name those coefficients. We'll call them A sub alpha and A sub beta. These are going to be our gauge potential. So it's a simple reorganization, and you get this, this result for the A sub alpha and the A sub beta at the bottom of the screen. You see where the minus signs are coming from. It's coming from moving the alpha dot and beta dot terms to the right-hand side of the equation. Okay, so I already said that how theta changes now depends on where we are in shape space. But we've also gotten to a more complicated, richer shape space. The shape space is defined by these two coordinates, alpha and beta. So in addition to drawing the real picture of the cat here, I'm going to start drawing the shape space as well, so we can look at both of them together. So in the bottom left of this slide, you see my shape space. And we've been thinking about the alpha, the first angle we introduced, as going from 0 to 2 pi. The cat could move that muscle all the way around. And similarly, with this new blue mass, the beta can go all the way around. So in essence, our shape space is this dashed square in the diagram going from 0 to 2 pi in each axis. At the top of the slide, I've just summarized our results again from the last slide that related the orientation angle to the shape angles, and we get these gauge potential coefficients. Okay, what is this all good for? Well, just as before, you'll notice that the time cancels out of this relation, and we get a differential relation. So that means something really interesting. As I move from one shape of the cat through my shape space to another shape of the cat, it doesn't matter how quickly I make those changes. It doesn't matter if the cat really, really quickly shifts to here and then slowly shifts to here, or vice versa, or goes slow the whole time. None of that matters for how its orientation changes. Its orientation is purely related to what the shape coordinates are. So this is what makes us call this a geometric phase. This is something that's related to the geometry of the problem, not to the dynamics of the problem directly. So that's why I was emphasizing this in the first time we saw it. This canceling of the time is really interesting. In the context of quantum mechanics, you may have encountered this as a Berry phase. The Berry phase is a quantum mechanical version of this same phenomenon. Okay, but we're just going to do the same thing we did before. We're going to take this relation, cancel out the dt's, and integrate both sides. When we integrate d theta, we get the finite change in theta. And what we're saying is that you can calculate that finite change in theta by integrating the gauge potential, well, the component A alpha against D alpha and the component A beta against D beta. So what I want to do now is try this. Like let's make some shape changes of our cat, and let's see what those shape changes result in terms of orientation changes. So just to make things concrete, the thing I'm going to try is illustrated in the shape space on the bottom left here. And it's a path. I'm going to try making a closed path in shape space. So the first leg of the path goes from the origin. The origin means alpha equals 0, beta equals 0. So it means the cat has all of its mass completely aligned. It's like in this the first part of this right panel. So then we're going to move so that the green mass and the red mass separate until they get to pi over 2. And then we're going to separate the blue mass from its alignment with the green mass until they get to pi over 2. And then we're going to go backwards. So that's the closed path we want to consider. And the neat thing I want to show you is that we can actually calculate how the orientation of the cat changes for every single one of these. So consider the first path, the one I've labeled 1 here. And we're going to calculate delta theta 1. It's just the integral. Well, along this path, alpha is the only one that's changing. D beta is 0. So we get to ignore that term. And we'll integrate from 0 to pi over 2 of this thing. But remember, we're also always on the level set where beta equals 0. So I want to evaluate this A alpha at beta equals 0. Evaluated at beta equals 0, these terms are just 1. The cosines are just 1. So I get 5 over 6. And when I integrate d alpha, I get pi over 2. So 5/6 of pi over 2 is 5 pi over 12. And we've gotten a calculation for the change in orientation. The orientation apparently goes to negative 75 degrees. Again, why did this happen? Well, it happened because the angular momentum of the cat had to stay 0. So as I was changing the shape, as I was moving the green and blue masses away from the red mass had to move backwards in order to compensate that. Or as I was doing it, I mean, as the cat was doing it. And you can see that the green and blue masses, they have larger moment of inertia. So they change position less than the red mass does in order to preserve the total angular momentum equals 0. And indeed, we've got a shift in orientation of our cat. Okay, but we want to know, can we really do the cat phenomena? That is, can I take the cat's initial shape, take it around some loop in shape space, bring it back to its initial shape, but have changed its orientation? So that's why I'm choosing this closed loop here. And I won't use it right away, but the reason I've labeled the interior here is I also want to be able to refer to all the shapes that are interior to that loop. So I'm calling it omega. I'll talk about that later. All right, well, this is now an exercise for you to do. I ask you to prove all of the following. Calculate that same integral we just calculated for every leg of the path. For the part 2, we get this first result. The part 3, we get this second result. And I'm sorry, I have a typo here. I mean the leg 4 in this last part. And we get this result. And just so you can follow even graphically what's going on, even if you haven't done the calculations yet, The idea is, as we said, we start out with the cat totally aligned. Along the first path, it goes to this 75-degree change in orientation we just mentioned. Along the second path, the blue mass becomes perpendicular to the green mass's direction, and the orientation changes backwards more. Then we bring the red mass back to the green mass, and the orientation changes, this time positively. And then we bring the blue mass back to the alignment, and the orientation changes by 27 degrees. But lo and behold, the miracle, the cat is not back where it was orientationally. So even though its shape has returned to an aligned shape, its orientation is shifted. So this is the striking thing that this model captures. So we're going to kind of try to understand this more and more deeply, but just to summarize, the calculation showed the total change in orientation is just the sum in the changes in orientation along each of those legs. And if you add up all the numbers I've shown you, we get this non-zero change in orientation that I'm illustrating in the picture. Okay. So a real cat is obviously even more complicated than that toy model that I've just shown you. And so it has even more degrees of freedom in how it changes shape. But you can now see what Mary saw from these pictures, and this is a very beautiful version of that. So the cat starts curled. As it begins falling, what it does is it stretches out. It uses that stretching to help it change its orientation, and then it recontracts. So it goes from roughly the same shape initially, and finally, through it changes in shape, it manages a change in orientation, all the while constraining its angular momentum to 0. So I think it's a beautiful physical example, but it's also a really nice introduction to gauge theories. All right. A couple of more technical points about this. These are points that we're going to kind of use as we move forward, probably past today. But I want you to notice that while I drew it as a nice planar shape, this shape space that we were just studying is actually a torus. So as we go all the way around from 0 to 2 pi in the alpha coordinate, that we actually arrive back at the same place, right? If we took the red mass all the way, or sorry, the green mass away from the red one all the way in a circle, we'd come back to where we started. And so you should actually think of the origin and this point as being identified. Well, in fact, you can do that at every height on this. So the left edge and the right edge are identified. But in exactly the same way, as we take the blue mass away from the green mass, we're going along the beta coordinate, and beta equals 2 pi should be identified with beta equals 0. And that's true all the way along the bottom edge, all the way along the top edge. You make the first identification, you get a cylinder. You make the second identification, and you get a torus. And so the shape space can also be thought of as this topologically non-trivial torus that I'm illustrating on the right here. In fact, often on torus topology, it's really useful to have these track these two independent cycles. So I'm going to call the path that goes all the way around in the alpha axis the A cycle, and that's what I've illustrated on the torus here. And the one that goes all the way along the beta axis, I'll call that the B cycle, and it's the meridian on the torus that I've pictured at right. So yet another exercise for you to try to see if this is all making sense to you is to repeat these calculations of delta theta for integration just along these two cycles that we just identified. And again, because they're cycles, I'm going to give away part of the answer to this question. The shape goes all the way from being one value, say all masses aligned, back to that value as you go along this cycle. But you get non-zero changes in orientation. So part of the way to think about what's going on here is to think about the topological non-triviality. Okay. So we are starting to gather that differential forms are quite useful. And that's actually the first and maybe primary lesson I want to take from the cat, is that writing things in terms of differential forms can actually quite aid you in calculations. So each time we worked with different models of the cat, we always found that you could write d theta in terms of some combination of coefficients times the shape coordinates. As we move forward, we're going to do this again and again. And in space-time, you can think of this, this differential form. I'm going to write differential forms with just normal undecorated letters. You can think of the differential form as its components times differentials in whatever coordinates you're using. So for example, in space-time coordinates that we'll use a lot, where mu is running over time and the three spatial indices, you can think of your potential one form as the contraction of those components with the differentials of the coordinates. One of the basic operations in the theory of differential forms is to take their exterior derivatives. And the exterior derivative means take this one form and compute the derivative of its first component and wedge that with the thing that was already there. And then you can also write this here. I'm using Einstein summation notation. So I'm summing over these A and B indices. The reason I'm taking A and B to be 1 and 2 here is I'm just trying to give you the example of the cat. So I'm thinking of A and B as labeling alpha and beta. But as I was saying, you can use any kinds of coordinates you want for this kind of process. It turns out that if you do this calculation carefully, the summation over A and B means that you should put a 1/2 in front and work with this combination. All right. So, so differential forms are leading us to yet another object, the exterior derivative of our potential one form, and we call this thing the field strength. So let me try and convince you that the field strength actually is interesting. I promised to tell you a little bit more about the wedge product, so that'll give context for what I'm about to say about the field strength. So wedge product is a beautiful and simple construction. Many Europeans learn it instead of the so-called cross product. It's somewhat analogous, but it's actually much better. Unfortunately, I was born in the United States and we teach cross products, so I didn't learn this till much later, but it's simple and beautiful. The wedge product, it works on any vector space whatsoever. And the main property, and it's almost, this is almost a complete definition, is that if you take two vectors of the vector space and you form a wedge B, that's necessarily anti-symmetric. So if you change the order of the two products, the two vectors in the product, you get a minus sign. This gives us a sort of generalization of a vector. We're going to work with these formal symbols that have wedges of multiple vectors in them. And when you have just two vectors in it, we call it a bivector. And it's very easy to interpret what it means geometrically. It's just an oriented area. So you form the parallelogram made up of the first vector you had and the second vector you had. And the wedge, A wedge B, is the bivector, which is this area given by the magnitudes given by the area of this parallelogram, and it's oriented. And that's partly what this minus sign is about. And you can think of the orientation as being the rotational sense that would take you from A to B. So if you were learning a cross product, the way we would say this is you put your fingers along A, you curl them towards B, and your thumb points in the direction of the cross product. We're not doing that here. We're not going to use the thumb. And the reason is the thumb is intrinsically three-dimensional. You're going into 3 dimensions as soon as you do that. This wedge product is oriented without going outside the plane of its definition. And because of the minus sign that defines this wedge product, well, the other orientational sense just comes from putting B before A. So B wedge A is you rotate from B to A. You can see that these are just the same parallelogram, in other words, the same area, but different rotational senses on it. Okay, I said this is the defining property, but it's hard to compute immediately. At least my intuition doesn't tell me exactly how I should compute with this definition. But I want to show you that it's actually quite simple. The idea is you just expand the vectors in any basis you like. So let's choose a basis E1, E2. You could imagine the horizontal direction is E1 and the vertical direction is E2. And write out the vectors in that basis. So we have component A1 times E1 plus A2 times E2. And then you just formally combine things in the way that this rule says. So you distribute like you would for any product. And the first distribution gives me A1 times B1 with E1 wedged into E1. But E1 wedge E1 is minus E1 wedge E1. What's the only thing that's minus itself? It's 0. So any vector wedged with itself gives us 0, and that first term vanishes. And then we can go to the second one, and we get A1 B2, E1 wedge E2, and you see that's this first term I've written on the right here. The second term, well, it's A2 E2 wedged with B1 E1. That gives me A2 B1, but it's E2 wedge E1. But how do I straighten that out? I just swap order to get a minus sign, and that's where this minus sign came from. So the remarkable thing about wedge products is all you need is the anti-symmetry, and you can just do every calculation based on that anti-symmetry. So once you kind of get used to this, it becomes more and more easy. But I think at first it's like looks mysterious, but it's really quite simple. E1, E2 being basis vectors, they have unit length. And so E1 wedge E2 is just the parallelogram that's oriented the same way and has unit area. So what we're getting is this quantity times something with unit area and this orientation. But what is this quantity? It's exactly the area of the parallelogram. So in the end, the result is that we're getting the area of the parallelogram times this orientation. So this wedge product works incredibly well, super beautiful. All right. This is the heart of the technicalities. I'll go through this and then pause because I imagine questions are going to be plentiful after some of this. So you may have also noticed that in that formula we were just looking at, this one at the bottom of the slide, in that formula, you'll see that that coefficient is precisely the determinant of this little matrix where we've put the components in the columns of the matrix. This observation is actually quite useful. What it means is if we do any linear transformation, let's call it T, and let's just act this linear transformation on our bases. So let's act T on the basis E1, E2 to get the new basis F1, F2. And let's see, what does that do? Well, we can check just by forming the wedge. F1 wedge F2, well, that's the linear transformation acting on E1 and E2. So the linear transformation picks up these components. And then the linear transformation acting on E1, E2 with the other components, the two components here to give F2. And you'll see that this is exactly the calculation we just did. In other words, the coefficient of the result is going to be the determinant of this linear transformation. So in fact, this is the geometrical way to define the determinant in any number of dimensions. You simply form a wedge of basis vectors, you act a linear transformation, you form the wedge in the new basis, the resulting basis, and they're related by the determinant. This is going to be immensely useful for doing calculations with differential forms and more generally in general relativity. And this connects with things you've seen in your general relativity classes. You probably introduced a so-called volume form. So I'm just going to use, as I said, all differential forms in today are going to be kind of undecorated. So I'll just call the form vol. And how's it defined? Well, the standard volume form is the square root of the magnitude of the determinant of the metric times the wedge of all the differentials of the coordinates. Here I'm imagining we're working on an n-dimensional, little n-dimensional manifold. Okay, but now let's see what happens under a coordinate transformation. Let's imagine that we change from the unprimed coordinates to the primed coordinates via this linear transformation. T with a mu prime upper for the new coordinates and the nu lower for the old coordinates. Well, according to what we were just calculating, that means that this differential here, dx1 wedge all the way up to dxn, should transform by the determinant of that transformation. But, and this is the whole reason for introducing a volume form, the volume form should be invariant under such transformations. And this explains, if you ever felt any mystery about what this prefactor is doing here, this square root of det g, this explains why. It turns out, and this is another exercise for you to check, the square root of det g under such a transformation transforms as the determinant, the inverse determinant. And in this calculation, we now see that the inverse determinant coming from the metrical factor and the determinant coming from the wedge factor cancel each other. And indeed, the volume form is invariant under such transformations. Just to give you a hint on how to do that calculation, imagine evaluating G on various basis vectors, and then how to transform those, see how the G transforms under that change in coordinates, and then calculate the determinant and see how this works. All right, so we're already seeing that the wedge product helps us see some of the simplicity of the calculations behind some of the technical things that we do in GR. Okay, just to illustrate this a little bit more concretely, a little bit more specifically, let's see how it works for polar coordinates. So I have my Cartesian system xy here, but I'm also going to think about the polar coordinates r and theta. The area of any little region in this plane is, of course, just dx wedge dy. That's the differential version of the area. And it's familiar. This is the thing that you've always integrated to get finite areas. And according to what we were just saying, that should be equal to the determinant of the metric square rooted times our new choice of coordinates, dr wedge d theta. And in the polar plane, you're probably familiar with the fact that the metric is just 1 in the r direction and an r squared in the theta direction. So we plug the determinant of this, which is r squared, into this formula, and we get the usual area form on the polar plane that you've seen lots, r dr d theta. Again, the presence of the wedge here shouldn't disturb you at all. It's just saying that I'm keeping track of oriented areas. So dr wedge d theta is different. It's negative d theta wedge dr. All right. So I said in words very briefly, but I kind of blew past the subtlety in this definition of the field strength that we saw a few minutes ago. So here's our field strength. We defined it as the differential of our gauge potential. And I claimed that it was equal to this. But this has this funny factor of 1/2 that on first sight you might not be convinced by. And this factor pops up in a lot of calculations and can be a little confusing if you don't understand where it comes from. And so I'm just going to show you very concretely where it comes from in this particular instance. So we want to also work with f as a tensor, not just as a differential form. And so let me ask the question, what are the components, the tensorial components of the field strength? And when we ask about components, we almost always mean that we want to know the components in a tensor basis. So what do we mean by the components of f? We mean indices to keep track of all the pieces of f. But the basis part, the thing that describes what f is the dxa tensor dxb, unlike the wedge. This is not the wedge. So what are these components, FAB? We want to actually use them and compute with them. And I'm going to just guess and show you a calculation that proves my guess. That you might be bothered by that logic, but it's a little simpler to do the calculation this way. If you want, once you understand the calculation, you can turn it around, run it backwards, and it gives the same result without any guessing. But here's my guess. I'm going to guess that these components are this thing in parentheses without the 1/2. And let's see why that's correct. So we defined f this way in this wedge basis. And so I've made this guess, so I'm just going to plug this guess in. But what does the wedge basis mean? We said that the wedge basis is always antisymmetric in its factors. So if you re-express that in a tensor basis, it means that I take dxa tensor dxb minus dxb tensor dxa. Okay, and I'm using Einstein summation, so little a and b are being summed over. And let me just distribute the f over these factors. Once I've distributed, I have this result here. And now this second piece, well, these are just dummy indices. So if I want, I can relabel my dummy indices. So A, I can relabel it to B, and I've done that. And B, I can relabel it to A. Fair enough. So having done that, now my basis element is the same in both expressions, and I can factor the basis element back out. So we have 1/2 FAB minus FBA times this tensor basis. But you can see from the definition of the FAB, that, or the guess of the FAB that I took, that this expression is antisymmetric. That is, if I swap A and B in this expression, I get a minus sign. So what is FAB minus FBA? Well, it's just 2 times FAB. That 2 cancels the 1/2, and I perfectly get the right components in the tensor basis. So this is the proof that in the differential form basis, you need this 1/2 to get the right components in the tensor basis. More generally, I've shown you this whole calculation for a 2 form. More generally, it's going to be a 1/p factorial, and I leave that for you to check. All right. Just 2 or 3 more technicalities, and we'll stop for questions. I introduced the volume form just now as a differential form and sort of contracted thing that isn't really in coordinate components like we usually work. And sometimes it's useful to break it up into pieces and think about it in different ways. So one of the most powerful tools for doing that is the Levi-Civita symbol. And the Levi-Civita symbol is just defined as an all-index down object that is +1 if all of these indices are an even permutation of 0 through n-1. Here again, I'm imagining an n-dimensional space or space-time. It's -1 if it's an odd permutation of those things, and it's 0 otherwise. You probably have seen this thing a lot, but I wanted to emphasize 2 things about it. It's called a symbol because it's not a tensor. We're carefully calling it a symbol here because it doesn't transform like a tensor. However, much like the wedge project, it's completely antisymmetric. If we permute any 2 of these indices, it goes from +1 to -1. And that means it's closely related to a determinant. In fact, it's essentially just the same proof that we looked at a moment ago for the wedge to show that epsilon in a primed coordinate system is the determinant of a linear transformation. That product is the same as epsilon in an unprimed coordinate system times all of the linear transformation matrices. So it almost is a tensor. You see the way in which it's failing to be a tensor? The right-hand side looks like a tensorial transformation. And the only thing that's failing to make it a tensor is this determinant factor. So let's bring that determinant factor over to the other side and think about it as a coordinate transformation. So if we really think of what we're doing as a coordinate transformation, then these T matrices are the Jacobian of the coordinate transformation. And we see that 1 over the determinant, well, that's determinant of the inverse matrix, which is exactly the Jacobian the other way around, the inverse Jacobian. So this object fails to be a tensor only because of the power of this determinant that's appearing in front of it. And these kinds of things come up a lot. And so we call such objects densities or tensor densities. And the notation that we use is to put a tilde over the object and use indices to indicate that it's like a tensor. It has indices that transform in the multilinear way that tensors do, except that it also has this power. And it's the power of this Jacobian, the primed one with respect to the unprimed, that we call the weight of this tensor density. So in this example, we have a tensor density of weight 1. You can now see why I'm giving you this particular technical information. I told you last class that I was going to introduce Ashtekar variables for you, and that Ashtekar variables were a densitized triad. So now you know what I mean when I say it's densitized and why I put this tilde on it. It's because it doesn't transform exactly as a tensor. It carries factors of the determinant of the coordinate transformation with it. All right, end of technicalities. I used the mathematician's closed proof box to say, okay, we're done with that. And let me go back to why do we care about the field strength, and then we'll pause for questions. So the field strength is another way to do these calculations that we just did with the change of orientation of the cat. The field strength is the exterior derivative of our gauge potential, and it turns out, you remember our little region omega, the little box that we went all the way around? You can find delta theta by integrating the field strength over the area of that little square. That is, over the full area. And it's a nice calculation, and you can check this yourself. So compute d a beta with d alpha, subtract off d a alpha d beta. I'm just writing this out explicitly. Integrate that over this area, and you'll find exactly the same delta theta that we did before. The reason for this is one of the major advantages of differential forms, and I expect you've seen this a lot, so I'm just going to state it. It's just Stokes' theorem. So the regional integral of a two-form f, well, that's just the regional integral of dA. But according to Stokes' theorem, that's the closed loop integral of the one form A around the boundary of that region. So this is the proof that indeed these two integrals give the same result. So the field strength gives us a second way to calculate changes in orientation for the cat. All right, just a comment about gauge theory. For our second more complicated cat, we have even more choices of body axes. I showed you the red body axes and the green body axes, but now we could also choose blue body axes, axes that are lined up with where the blue mass is pointing. And if you do this, and I'm leaving it for you to do as an exercise because it's a nice one, the relationship between the blue orientation coordinate and the original red orientation coordinate is now actually a function of both the shape parameters. To relate them, you need to use both alpha and beta. So I'm calling the thing that does that relation lambda. It's a function of alpha and beta that gives the relationship between this different gauge choice. But just as before, we can calculate the gauge potential for theta prime. So it'll be some new gauge potential. D theta prime will be A alpha prime D alpha and A beta prime D beta. And if you just follow that definition, well, what are these components? They're just A alpha plus the partial derivative of lambda with respect to alpha, and similarly with respect to beta. And now you see something really cool and interesting. The field strength, which you'll recall was just dA, the field strength, well, when you plug in what A prime is, you get back our initial definition of F, plus you get second partials of lambda. But when you track how the second partials show up, you see that they're both acting on lambda, and it's just the equality of mixed partials cancels out. So this field strength that we were just computing, F, is gauge invariant. Even though A changed, F does not. So that's another major advantage of the field strength. It's a gauge invariant description of the change in orientation. I just did this in coordinates so you could see it, but of course this is a place where the differential form language is massively powerful. So what am I saying? I'm saying that under a gauge transformation, the gauge potential changes by a total differential, d lambda. D alpha lambda and d beta lambda are just the components of that total differential. And what is F? Well, by definition, F is the exterior derivative. So we get dA plus d2 lambda, but the second exterior derivative vanishes identically. And so this is another proof of the invariance of this field strength. If you aren't familiar with differential forms and you've never seen this kind of calculation, d2, the squared exterior derivative, is always 0. What's the proof of that? Well, it's exactly the equality of mixed partials. It's just in a more complicated, you can do it for any coordinate system, but it always boils down to the equality of mixed partials and the fact that when you do them with different signs, they just cancel each other. All right, that's a little over half. And so I'll pause and check for questions. I see that there's some already in the chat, so I'll start with those. The first one says, could we have an orientation manifold with curvature? I might need a little bit more context for what you're asking here, but I have been assuming that our manifold is oriented. Doing GR on non-oriented manifolds is a bit tricky, but you can still discuss curvature in that context. It's just that I don't think we know how to make sense of what it would mean for space-time to be non-oriented. So we usually don't consider that for physical reasons. But feel free to follow up if there's something that more to your question. Why is the volume not oriented whereas the surface is? Sorry if I gave the impression that it wasn't. Maybe that's what the first question was about also. Let me go back to the slide where we were discussing the volume form. It is also oriented. It's through exactly the same mechanism. It's these wedge products that are keeping track of the orientation. So I illustrated everything with the case of a single wedge product that is going to a 2 form just because it's so easy to keep track of and easy to draw. So this is, you can see exactly what I mean when I say this. But it turns out the wedge product continues to do this as you go to higher and higher dimensions. So if I formed the wedge product of 3 differentials, it turns out I would naturally get a right-handed volume form in that 3-dimensional space. And it would be the negative of the left-handed volume form in that space. It's just hard to draw how it is that the wedge product does that. But it's doing it through the same anti-symmetry that we saw in this 2D case. If you switch, we have dx, wedge dy, wedge dz. If you switch any 2 factors, you get a minus sign. And switching those 2 factors is exactly going to a left-handed orientation. So it works perfectly. All right. Another question that came up was, what kind of coordinate transformations could we have in manifolds with many singularities? Deepan, that's a nice question. Towards the end of today, I'm going to talk about the tetrad and triad formalism. partly because it's getting to these Ashtekar variables that we're going to use. But another feature, which I wasn't planning to discuss today, but that you're raising, is that by working with the tetrad, you can actually allow for singularities. In other words, you can allow for the determinant of the tetrad to be 0 at a point of space-time. And at that point, it's as if you have no metric anymore. And it's as if that's a singularity. So the tetrad formalism actually kind of allows for a bigger class of manifolds than the usual metrical formalism. Whether that generality is essential to quantizing gravity or not, no one knows yet. But it is a flexibility of the so-called first order formalism that is very interesting and that we think about a lot. All right, Diego asks, the CAT system had to satisfy some requirement to use the differential form formalism. He's saying, was it special to the CAT system that we were going to be able to use differential forms? And the answer, Diego, is that no, it's not special to the CAT system. We can do this quite generally, and we're going to see it in electromagnetism. But it does sometimes require you to rethink your choice of variables. So in electromagnetism, for example, in undergraduate studies, we usually treat the electric and the magnetic fields as vector fields. It turns out we're going to have to think of them as forms themselves in order to use this differential formalism. But there's no problem in doing that. You're probably asking a more complicated question, which is how do we know ahead of time whether we can do this or not? And I actually don't think there's a great answer to that question. There are some partial answers, but if you hand me a physical theory and you ask me, will you be able to cast this as a gauge theory? It's not obvious from the outset whether I'll be able to figure that out or not. And so part of why I'm spending time today on discussing this is that it was kind of a non-trivial, a rich and interesting and exciting achievement to cast GR as a gauge theory in the way that we're going to do it. So in general, I don't have a slick answer to your question about can we prove whether you can do this or not. But it's quite common, and all of the fundamental forces do have gauge theoretic formulations that you can write in terms of differential forms. So that's nice. Faikal asks, what is the gauge invariant in the second model of the CAT? So it's in fact both the shape coordinates, alpha and beta, that provide gauge invariant quantities. It's partly what I mean when I split up our coordinates into shape coordinates and orientation coordinates. The shape coordinates are the gauge invariant quantities, while the orientation coordinate depends on your gauge choice. But I don't want to confuse you that they're the only gauge invariants. You can compute other things that are gauge invariant. For example, you could even just take combinations of alpha and beta. Alpha minus beta will also be a gauge invariant. So it's actually part of your interest as a theorist to come up with the good observables, the good things that you can measure easily that are gauge invariant. And in electromagnetism, for example, the electric field and magnetic field are those good things. So this is definitely an interesting question and one that we often pursue. Maybe I'll do one more question and then we'll jump into the second half. Chadzifotis asks, usually the use of differential forms is fixed on a holonomic frame. Does one get any geometric non-trivialities in non-holonomic frames? That's a lovely question, that I'm a little worried, since I haven't introduced holonomic, and that gets into a whole story. I'm a little worried to get into this sort of technicality right at the moment. So I'm going to leave that one for the future. But there's definitely interesting things about this this question. I'd recommend Harley Flanders' book on differential forms that talks about this kind of question. Also, Shlomo Sternberg has a nice treatment of some of these things. All right. So just to remind you where we are, the second part, I'm going to take up electromagnetism. I like the cat example so much just because I feel that I really understand every part of what we mean. We're talking about these kinds of changes in shape, and we really know there's no abstraction about what the gauge potential is doing. It's quite concrete. It's helping us calculate changes in orientation and so on. In electromagnetism, we're still in a very physical theory that you know very well, but already we start to get a little bit more abstraction. It's a bit harder to say, for example, what the gauge potential does. I will give you a brief statement about that towards the end of the section, but that's why I started with the cat. It's so clear what's going on. Nonetheless, formulating electromagnetism as a gauge theory is extremely powerful and interesting, and that's what we want to do as our final warm-up to doing it in GR. Okay, you all were asking these nice questions about how do we write things in terms of differential forms? How do we know if we can do this? And electromagnetism is also a good example of how we go about doing this. So you know from having done a lot of EM calculations that fluxes, like the magnetic flux through a surface, come up a lot in applications. And so fluxes, well, those are integrals of the magnetic field over the surface. And so it sort of naturally suggests that we should be working with a two form for the magnetic field. So I'm going to write down the electric and magnetic fields as forms. Here, my notation is that you could think of EX, EY, and EZ as the usual components of the vector field that you're familiar with. But what I'm going to do is I'm going to pair them with differentials instead of as components of a vector. And so we build an electric one form this way, just pairing EX with DX and so on. And a bit surprisingly, I'm not going to do the same thing with the magnetic field. Instead, I'm going to pair BX with a two form, which is dy wedge dz, and so on for the other components as written here. And it's a natural and immediate question, wait, why aren't we treating them the same? And why these particular choices? What is it? What's making this happen? And the answer is quite beautiful and actually quite simple. We want to try to write Maxwell's equations in this differential form language. And you can show that if you take D of the one form E that we've just introduced, you get a two form, and the components of that two form are exactly the same as the components of the curl of E. And similarly, if you take D of the two form B, well, there's only one component now, and that also makes sense because we're working in a three-dimensional space, so we only have one three form on it. And the single component of dB is the same as the scalar, which is the divergence of B. So by making these choices of forms, the D's of the two forms that we've introduced are immediately capturing aspects of the Maxwell equations. In fact, if we take the static limit, that is the limit in which none of these components, E's or B's, depends on time, then these are just the Maxwell equations. The curl of E equals 0 and the divergence of B equals 0. And we can write that in differential form language immediately as dE equals 0 and dB equals 0. So we've done two things. We've reformulated the fields as forms, And we've discovered the first two Maxwell equations in the static limit as differential form equations. So it's a really nice formalism. Of course, we want to do this not just in the static limit, so let's try and do that as well. So I'm going to again introduce a field strength, and the field strength, well, it should involve all of our space-time coordinates, and so let me promote not just the B as a two form, but let me take E and wedge it with dt. That now makes this thing, E was a one form, it makes this whole thing, E wedge dt, into a two form. And maybe you're not too surprised now to see that I can rewrite that as 1/2 some tensorial components wedged with the general two form dx mu wedge dx nu. So again, Einstein summation convention is in effect. A couple of quick comments about conventions. I'm now setting c equals to 1, just like I did with the mass and the radius above. I'm working in Heaviside Lorentz units. These may be less familiar to you, but they set all the epsilon naught mu naughts in the SI units to 1, and they also get rid of all the 4 pi's in the Maxwell equations. The 4 pi's all get stuffed into the Coulomb's law and things like that, the force laws. And just for convenience, I often will just immediately write x0 as t, just so you can kind of get your space-time intuition. So with these various definitions, the field strength, this two form that we've just introduced, its components you can work out, and I encourage you to do it. And they're given by the field strength tensor that you may have met if you did any relativistic electricity and magnetism. So it's anti-symmetric. You see there's negative E along this first row and E along the first column. And the B's are displayed here in a nice way, but again, the anti-symmetry under the transposition is evident. So if you use this two form F that we've just introduced, both of those two Maxwell equations that we were just discussing can be written in one single equation, which is that dF equals 0. You might be a little surprised that we were able to take two equations and rewrite it as one, but the reason is exactly what we're seeing with the time slipping in here. The B field part of this ends up with no time component, so the vanishing of dF gives the dB equals 0 part. And the E always has a T component, and so the vanishing of dF gives the E part as well. So again, this is an extremely succinct way of writing Maxwell's equations, the first two. Okay, but let's relax the static assumption. So instead of thinking of the E's as only depending on space and the B's as only depending on space, we're going to allow them to depend on space-time. And let me make a definition. It's just a convenient notational definition. I'm going to break the exterior derivative up into two pieces. I'm going to call one the spatial exterior derivative, d sub s, and the other part I'll call the time component, although it's defined this way. So what I'm saying is the space-time exterior derivative, dB, can be written as dsb plus dt wedged with the partial time derivative, just the usual partial of components of the two form B. So what does that mean? I just take the coefficients of the two form B, I take their time derivatives, and that gives me what I mean by this two form dTB, partial TB. And again, more concretely, what I mean by exterior derivative, well, take a partial with respect to a spatial coordinate and take dxi wedged. So big I here is what people call a multi-index. You can imagine x dy wedge dz. So this would be partial with respect to I of bx. This would be the dx part, and this would be the dy wedge dz. So the multi-index is keeping track of forms of higher rank. Okay, but just to get out of the formalism for a second, say, what does this mean? Well, this first one is going to give us exactly the divergence part, and the second one is going to give us the time part. The divergence part is spatial, and so this makes sense. The spatial exterior derivative is giving us the spatial part, and the time part is giving us the time part. Okay. Why some extra notation here? Well, it captures the non-static, the evolving in time version of the Maxwell's equations, and they're just exactly the same as before. In other words, setting df equals to 0 is going to give us both time-dependent, both of the first two time-dependent Maxwell equations. So let's prove that. df is just, by definition, dB plus dE wedge dt. But we can break up the exterior derivative into spatial and time pieces. On the E, when we break it up, there's the spatial piece and there's the time piece. But when we do the time piece, we'll get dt wedge dt, and the antisymmetry kills that term. So only the spatial piece survives. And then we just collect terms that have similar wedges in them. This is completely spatial, and so we conclude that dsb equals 0. And this, both terms have time pieces, and we collect the coefficients of those time pieces, and we get dt of the two form b plus the spatial exterior derivative of e. Remember, e was a 1 form, so this is a 2 form, so this equation makes sense. We get that that vanishes, and we have the time-dependent first two Maxwell equations. That's a really nice formalism. All right. One of the reasons we're doing electromagnetism is you have a little bit more intuition, and I can introduce more notation that we can then use later on down the road. We're going to need all of it. So one of the things we're going to need is the Hodge star. And the Hodge star is a sort of duality operation on forms. In particular, if you feed a p form, a form with p factors in it, to the Hodge star, then you get an n minus p form, where n again is the dimension of the manifold you're working on. To build a little intuition, let's just do a concrete, very specific example. Take flat R3 Euclidean space. Then the Hodge star of dx is going to be, well, x is a 1 form, so we expect to get a 2 form out. And it turns out it's just dy wedge dz, and so on for the other basis forms. Okay, but how do we know? What is the definition of this thing? The Hodge star is defined in an interesting way. You take two p forms, omega and mu, I've called them here, and you wedge omega with star mu. Well, omega was a p form, star mu, well, mu was a p form, so star mu is an n minus p form. When we wedge a p form with an n minus p form, we're going to get a total n form. And n forms, well, the most natural n form around is the volume form. So the idea of the Hodge star is to require that this wedge gives a multiple k of the volume form. That's the definition of the Hodge star. You can see it happening up here. If I took dx wedged with star dx, then I would get dx wedge dy wedge dz, which is the volume form on R3. So that's the idea. But I was careful, and I told you that there was a constant multiple of the volume form here. What is that constant? Well, of course, depending on what forms you had, they might have different numbers in front, and we want to get the number in front of the volume form correct. And we can do that by introducing an inner product on forms. The idea is simple. You just take omega and you write it as the wedge. Remember, omega was a p form. You write it as the wedge of p1 forms. Mu as the wedge of p1 forms f. Of course, more generally, you could write these things as sums of such things, but this inner product is going to be linear, and you can just expand out the sum from the outside. At any rate, once you have this expansion of omega in terms of these basis forms, the inner product is defined as Well, just feed the individual one forms to the metric, really the inverse metric, and take the determinant of the resulting matrix. So it's just a generalization of the normal dot product to the factors of your p forms, and then you take the determinant of that, and that gives you the multiple of the volume form that you got. There's a slight technical thing that people often wonder about at this stage, which is, does the Hodge star depend on a metric? You are asking questions about Riemannian manifolds, and here we're working on a Riemannian manifold with a metric, and you see that this inner product on forms does depend on the metric. In fact, we use the inverse metric here. So this is one place where you need the metric. You also need the metric in the definition of the volume form, you'll remember. But you can slightly generalize the Hodge star and think about it, and it's interesting to do so. You technically only really need a definition of a volume form. It's just that the Hodge star will not be a form again. So if people have questions about that, I can talk about it more. But here for this course, it's easier, and we're not going to need the more general context. We'll always assume we have a metric around and define the Hodge star as I did here. Okay, why the Hodge star? What's the connection with electromagnetism? It's going to help us to compute the other two Maxwell equations. I also wanted to just make this a little bit more concrete because I think some of the wedge notation can get a bit abstract. So you remember we introduced the Levi-Civita symbol. It was a density of weight 1. That's why it had a tilde. There's a neat trick you can do, which is you can introduce a Levi-Civita tensor. You may have heard both of these are used around and been a little confused. Why do we talk about both things? Well, there is a tensor. All you do is you compensate that determinant factor we had before. So by compensating it, you get a tensor. This thing truly transforms like a tensor. And the reason I'm mentioning that is I can give you a very concrete expression for the Hodge star once we introduce this tensor, epsilon with all the mu's. The star of a p form A, well, it's an n minus p form. That's why it carries n minus p indices. It's just 1 over p factorial, the epsilon tensor contracted with the A that you started with. Wait a minute, Hal, you said all the epsilon indices were down. Well, again, we just use the metric to raise the first p indices, and those are the ones we contract. So you can think of Hodge A as the kind of epsilon dualized A. That's the sense in it. Well, that description of it makes it kind of intuitive and maybe not too surprising that if you dualize again, maybe you'll get back to the same thing you started with. And that's almost true. If we take a p form A and we Hodge star it twice, it turns out we get back A up to a minus sign. And the sign is minus 1 to the p, where that's the p form, n minus p, where n is the dimension, plus s, where s is the number of minus signs in your metric signature. So in Minkowski space, s would be 1, because we've been working in the signature minus 1, plus 1, plus 1, plus 1 for the Minkowski metric. So the Hodge star is going to turn out to be useful both here in electromagnetism and for gravity. Okay, so let me try and convince you of that. Calculation to do, a practice for your Hodge star is calculate the Hodge star of the field strength 2 form. And if you do that, you find in components that it looks like this. And if you go back and look at the slide that we had for F, or if you remember, it essentially has just traded B for minus E. There were minus E's up here, now they're B's. And E has gone into the slots that B was in. So it's kind of something, the Hodge star switches which field you're talking about, the electric and the magnetic, up to minus signs. And with that, we're actually in a position to do the other two Maxwell equations. So to put everything in nice form language, we introduce an electromagnetic current, one form. Our current is going to be the usual electric current, Jx, Jy, Jz, as a one form. But it's also going to include the charge density, rho, in the T slot. So the big J, the electromagnetic current, is going to be little j, the electric current, along with the charge density. And for you to check as well, but it's a nice repetition of the calculations we did above, you get the other two Maxwell equations now as star d star f equals j. So once again, we've compiled two Maxwell equations into a single differential form equation. And we have the very elegant pair of equations df equals 0 for two of the Maxwell equations and star d star f equals j for the other two Maxwell equations. All right. I've been telling you everything in the field language in terms of the electric and magnetic fields. And that was because I hoped that was more intuitive and closer to things you'd already seen. But now we can reformulate electromagnetism in this gauge potential language that we've been using. So the idea is actually very, very similar to what we did with the cat. We simply introduce a gauge potential one form, A, and we define the field strength as dA. So A here would be the A mu dx mu that we were mentioning. This is a really interesting move because it makes two of the Maxwell equations just trivial, immediately true. If you write things in terms of the gauge potential, then d of f, well, that's just the second exterior derivative of A, but we said the second exterior derivative always vanishes. And so df equals 0 is just immediate based on the variable A that you've chosen. So you've trivialized two of Maxwell's equations. You don't ever need to solve them again or think about them. They're just built in. The second pair of Maxwell equations are not trivialized, and you can just re-express them in terms of the gauge potential. We just plug in F equals dA, and we get them written in terms of the gauge potential. And part of what I want to point out here is that we see this gauge freedom that we saw in the cat. I can start with one gauge potential that, say, satisfies Maxwell's equations. Say you already worked it out. And I can get another gauge potential that will also satisfy Maxwell's equations just by design. And you can see that by introducing A prime, which is A plus d lambda. But now it's just immediate, right? F is going to be d of this, and the dA is there, and the d2 lambda is 0. And so it gives exactly the same field strength and will satisfy exactly the same equations. So in this differential form language, here lambda is a function of x mu, the gauge freedom is the differential of that function lambda. All right, so let's work this out in a little bit more detail. I've been staying at the high kind of theory level of just describing what the Maxwell equations are, but let's actually see this in practice. How does it all look? You take here, let's work in Minkowski space just to give you intuition for a second. Your one form is just going to be its components times each of your coordinates in that Minkowski space. And I'm going to use my gauge freedom. We said I could always choose another gauge by adding a d lambda. And there's an interesting gauge choice you can make here, which is just kill the first component. So that's what I'm going to do. In Minkowski space, that amounts to saying that A0 is just 0. Or if you're a little bit nervous, okay, Minkowski, we have all kinds of special choices with coordinates and things here. More generally, if you can make a space and time split, so there's a time and a space, but space might not be Euclidean R3, you can just say the same thing more generally by saying feed the one form A, the time derivative, and require that to vanish. Whatever that component is, it's going to be 0. That's what we mean by temporal gauge. And what I want to show you is that this really does give a set of Maxwell equations that we can think about and solve as differential equations. So let's work that out. Well, we've decided what the condition on our potential is. We're going to kill the first component. And what is dA? Well, we can do the same split of the exterior derivative. There's the time part and the spatial part. And if we look at what that means, you remember the electric field, well, it was in the other order, but it was essentially the thing that was wedged with dt. So that means the electric field must be negative dTA in temporal gauge. A here is this whole one form. So this time derivative is taking the derivative of all the non-vanishing parts of the gauge potential. And B was the rest of the stuff. And so B must be the spatial exterior derivative of A. So solving this as a differential equation would mean that you give me some data. We often call it Cauchy data. So you give me a gauge potential and an electric field at any one time. So you pick, in this space-time split, you pick data on the initial surface. And once you tell me that data, I'm going to be able to evolve it and find solutions at later times. Why am I making the space-time split? Well, eventually what we want to do is have a Hamiltonian theory of general relativity, and you need a notion of time for a Hamiltonian theory. That's what I'll be focusing on next week. But we won't stay only in a Hamiltonian framework. Well, the week after we'll go into spin foams, which is a path integral formalism as well. But this is a model for that Hamiltonian approach. Okay, so as we already said, the first pair of Maxwell equations are just trivial because of the whole setup. They're just immediate. But we can look at the second pair. And with the definitions we've just given, the second pair becomes the spatial part of the Hodge star, spatial part of the exterior derivative of E is rho. And this for, I won't read it out, this for the time part. So what I want to point out is that these two equations actually stand on a slightly different footing from one another. It's this first one, you see it doesn't involve any time derivatives of the fields. So it's actually a constraint. It says that if you give me E data, that E data better satisfy this condition or we can't do anything. We're not doing electromagnetism. So this is a lot like our J total equals 0 condition from the cat. It was just, we set the cat off with 0 angular momentum. It can't have angular momentum. And so the same thing goes for this first condition, which is just Gauss's law actually in disguise. If you work out what this is the divergence of E equals rho. And indeed, if you don't have that, we're not talking about electromagnetism. So that's a constraint. And it's true in the technical Hamiltonian constrained gauge theory sense. If you do all of the formal process, you find this is a constraint. On the other hand, the other equation contains the evolution part. So we can think of this as dt, evolving the electric field components given the A and E. The A is partly in this B. So again, I can just rewrite this last equation one more time. Remember in the last slide, we said that E was minus dTA. So if I want to evolve my given data, A and E, well, the first one evolves via this definition. It's just the minus E. And the second one evolves by sticking in what B is in terms of A. And so we get this evolution. So if you're good at differential equations, now you can actually solve electromagnetism this way. We've written out the evolution problem. It's very elegant. All right, so I've told you electromagnetism as a gauge theory, and I'm starting to run low on time, and I do want to introduce you to the gravitational part. So I'm going to skip this over for now, but just tell you why I wrote this, and you can come back to it and look at it. Remember, in the cat case, we understood that A was telling us a way to calculate the change in orientation. And what I want to mention to you is that in electromagnetism, it tells you also about a change in orientation, but it's a bit more abstract. It tells you about a change in the orientation of the wave function of a charge. In particular, the A computes for you the phase that the, say, electron wave function picks up as you drag the electron along a path in spacetime. So, there is a close connection with what we said about the cat for this gauge potential also. All right, in the remaining few minutes, I want to begin to introduce you to general relativity as a gauge theory. I'm going to just set up the variables. I expected us to be kind of where we are time-wise, so I'm just setting up the variables, and then we'll actually start studying it as a gauge theory next time. Okay. To do this, to write general relativity as a gauge theory, we actually have to shift away from something that you probably have taken for granted since you learned general relativity, which is that this fundamental field concept that I mentioned at the beginning today, that the field is the gravitational field, and that's the thing that's allowing interaction locally. You have become habituated probably to thinking of that field as the metric field, g mu nu, as a function of position. And my first message to you is that we're not going to do that. We're not going to think of the metric as the gravitational field. We're going to work with something else as the gravitational field. And this is motivated by two steps. One is a sort of observational step, like how do we do experiments in practice? And the other is Einstein's fundamental insight into the equivalence principle. So let me explain those two insights. Maybe some of you know, we had a very sad news the last month. The great Jim Hartle, a relativist who's done many, many things, worked closely with Stephen Hawking, and he just passed away. So I thought it might be nice to mention him and honor him here. And I wanted to do it partly because in his undergraduate introduction to general relativity, he has a beautiful way of thinking about observations in general relativity. So we know that space-time has become curved, and that that curvature means that gravitational field is different in different locations. So the question is, how do we do experiments? For example, how do we measure energy of a particle? And Hartle points out there's a very practical, pragmatic answer to this question, which is that we just set up a laboratory. So that's what's on the left hand. This is directly from his book, the left-hand picture here. We make our laboratory, and the laboratory should be small enough that there aren't huge changes in the gravitational field throughout the laboratory, so that we're kind of consistently working with one reference frame. But what does it mean to set up that laboratory? We just erect orthonormal axes in 3 directions. You could call the corresponding coordinates capital X, capital Y, and capital Z. And we put a clock on the wall, and we have everything we need in order to make local measurements in our laboratory. So if a particle comes through the laboratory, we measure how much it traveled, how much distance it traveled, we measure how much time it took for it to do that, and we have a notion of how it's moving. And we can even make this more concrete. What do you and I think of as the energy of that particle? Well, it's just the 0th component of its energy momentum 4 vector. And so how do I, as an observer, pick out that 0th component? Well, I just use my own 0th component vector to dot into that momentum to pick out that component. And what do I mean by my own 0th component? Well, I'm setting up my laboratory so time passes for me according to my wall clock, in other words, proper time. And that means that I'm using essentially my own 4 velocity as my time vector. And so the way we pick out local energy measurements is through dotting with our orthonormal frame vector E0. So what I think is so nice about this emphasis that Hartl's putting here, and that you should look in the book and see more about how he describes it. It's very nicely laid out. What I think is so nice about it is it's putting emphasis on the orthonormal frame, both the spatial piece of the orthonormal frame that we use and the time piece of the orthonormal frame. This is what we make our local measurements with. Okay, so that's half the story. How do we measure things? Well, we do it with a local orthonormal frame. The other half of the story is Einstein's insight into the equivalence principle. So we're working on a curved space-time manifold. That curvature means that we have to use very general coordinates to label points. So we just adopt completely arbitrary coordinates, x mu. But Einstein's huge insight, the sort of elevator experiment insight, was that you can always make a coordinate change in your local laboratory, right here where you're doing experiments. You can always make a change of coordinates to a freely falling frame. And in that freely falling frame, there's no gravitational effect. It's a local inertial frame. So let's call the coordinates of that local inertial frame, much like I was in the last slide, call them capital X. And here capital I is going to be ranging 0 to 4, 0 to 3, excuse me, and is going over our local inertial frame. And Einstein's insight about the equivalence principle can be cast mathematically as saying, well, we can take the local inertial coordinates and write them in terms of the general coordinates, and then do a Taylor expansion. And if we call the point P where we're doing that Taylor expansion our origin, then the first non-vanishing term in that Taylor expansion will be the Jacobian that goes from the inertial coordinates to the general coordinates. And this matrix, this Jacobian, is what we want to call the gravitational field. And that's very sensible. It's very interesting. It's saying that the gravitational field is the thing that takes you to the locally inertial system. Let's see how this idea, this is called a cotetrad, by the way. Let's see how this cotetrad is connected with the formulation that you're used to. The cotetrad, well, we can write it as a differential form. You knew I was going to do that. So EI, with I ranging, as I said before, is just the one form that we get by putting this Jacobian with a dx mu. And what does it do? It translates between the orthonormal frame that Hartle was describing that we make our measurements in, and the coordinate frames that our general coordinates use, the dx mu, the partial x mu vectors that build up the general frame of a general coordinate system. How does it do this? Well, it's a one form. You just feed that coordinate basis vector to it, and you get exactly this cotetrad matrix, this thing that translates between the two. That's the reason it's called the soldering form. In addition to being called a cotetrad, it's often called a soldering form. It's taking you from your general coordinate frame to an orthonormal frame. Well, we can compute inner products. That's what the metric does. So let's ask, what does it mean to calculate the inner product of two coordinate basis vectors? Well, that's just G acting on those two coordinate basis vectors. And that's the metric, G mu nu. But we've just said that this thing translates from the coordinate basis to the orthonormal basis. So we could, that's just components in another basis. We could compute this exact same dot product in the orthonormal basis. And by definition, it's orthonormal. So it has a flat Minkowski metric at that point. That's the equivalence principle. So how do we do the computation? Well, we just contract the translation with the a to ij, and we feed in the basis vectors to this soldering form. And what are we saying then? Well, if you contract the I and j indices with the Minkowski metric, you get back the spacetime metric. So this is the first and biggest step in our change of variables. And what is it saying? It's saying that the tetrad or the cotetrad here is like the square root of the metric. This is an interesting analogy. It's a qualitative statement. That's why I didn't say it on the slide. But do you remember when Dirac went to understanding the electron and positron field, he changed the variables he was working with. And that change in variables, he went to a sort of square root of the Klein-Gordon equation in order to get the Dirac equation and a good description of these fields. So what we're doing here is kind of introducing a square root of the metric. And this square root is going to be the thing that's our fundamental description of the gravitational field. All right, I'm almost done, so I'll wrap up. And then if Johanna has time, I'm happy to stick around for a few minutes and field
Yeah,
questions.
sure, perfect.
You can, of course, work with the inverse of the cotetrad. The inverse just means the inverse matrix. So if I contracted this with the cotetrad, I would get the Kronecker delta. But when you work with the inverse, you see the position of the indices just switches. And well, what does that mean? You can just rewrite the same ideas. You're translating now in the other direction. So you contract the space-time indices with the metric and you get the orthonormal frame metric. So the tetrad just goes the other way, translates into the orthonormal frame. So we refer to the orthonormal frame, the one in which we do our laboratory observations, as the internal space, and it has these capital Roman indices I and j, and as I said, the coordinate basis is the basis in space-time that you're used to and uses mu nu indices. And it makes perfect sense that our laboratory setup, our locally free-falling frame, uses Minkowski metric. Space-time is locally Minkowski. Furthermore, you know already that Minkowski spacetime you can boost, and it's a perfectly legitimate different choice of frame. And the Minkowski metric is invariant under that boost. So we actually have a gauge freedom here. This local and orthonormal frame that we're using, we can go to any Lorentz boost or Lorentz transformation. It could be a rotation as well. We can go to any Lorentz transformed version of it and still have a completely valid description of gravity locally. And so there's here Lorentz gauge freedom in this tetrad formalism. But what we're going to do, just as we did in electromagnetism, is make a space and time split. So we're going to imagine chopping space-time up into spatial slices. And it's not surprising that those spatial slices descend from the tetrad to what we call a triad. It's just a choice of spatial orthonormal frame at every point in your spatial slice. So the capital E variable that I mentioned last time and that we're going to study a lot as we move forward is called a triad. This time we changed letters just to keep track of the fact that we're on a spatial slice. Little I is the internal index. It's the orthonormal triad index. And A is our coordinate basis spatial index. And of course, these both range over just the spatial indices now. All right, the final step, again, we're making this spacetime split to do Hamiltonian theory. And the final step to the Ashtekar variable, which I promised you we would know by the end of today, is to densitize this triad. So here is the capital E, the triad variable we just defined, and we introduce a spatial metric Q, so that's just the analog of G on the spatial slice. We take its determinant and the square root, and we go from working with a triad to a densitized triad, something that transforms differently. I'll tell you more about why we densitized it, although I anticipated it in the first lecture. It was because when we work with this thing, areas become very natural variables in our theory. So I'll show you that more, but just to anticipate that, remember when we went into electromagnetism, we started working with two forms. And what we're saying here is that this thing is naturally associated with a two form, where you use the spatial Levi-Civita tensor to contract the two form indices with the densitized triad indices. So this full object is our Ashtekar electric field. So what am I going to do next time? Well, I promised you that I was going to show you that this is a gauge theory, and I've shown you half of that story. The electric field is going to be one of a pair of canonically conjugate variables that turn general relativity into a gauge theory. The second, you can guess already, is going to be a connection one form, but this connection one form now deals with spatial rotations. So you can think of it as an SO3, or better yet, as an SU2 gauge theory. And what I'll spend next time doing is really trying to build up for you some intuition about this connection, the Ashtekar connection. All right, thank you, and more than happy to field some questions.
Thank you, Hal, for the very interesting lecture. Yeah, we actually do have 3 questions in the Q&A. Would you like to take them?
Sure. Olafur asks, is there a reason to avoid the full-blown geometric algebra with its product? No, and it's lovely that you know about it. So the wedge product was in part developed by Clifford, many people in this time, and Clifford introduced another generalization of products of vectors called a Clifford product. And the Clifford product is weird in the sense that it combines vectors into things of different rank. So for example, if you take the Clifford product of a vector A with a vector B, you get a scalar plus a two form. And it's beautiful and very useful and well developed. Several people at Cambridge, several people have worked on it over many years. David Hestenes and Lazenby and Duran, others. And it's very nice, but it's very unfamiliar to people. I think even more unfamiliar than differential forms. And so far, nobody has used it to do something we couldn't do in other language. Although, you know, the folks who've worked on this a lot argue that they can really see geometrical results more easily using it. So your question is a good one. I myself have never derived a new result using it, and so I haven't like become a full-blown convert. But I do think it's worth spending some time learning, especially because this Clifford product shows up all over the place in Clifford algebras, which are very important for studying fermions. So I think it's interesting. I just don't know of any huge advantage we get from it yet. All right. Faikal asks, wouldn't the pointing vector be a 3 form in this case? So let's see. The pointing vector is E cross B in the standard formalism. And so yes, I agree. It would most naturally be associated. It would be associated with a 3 form. The natural 3 form would be something like E wedge B, but we're going to have to dualize in there because we know that the components of the pointing vector are vectorial components, so we need 3 components. So I'm sorry, I've never thought through this myself, but I suspect there's going to be another Hodge star somewhere in there to get the full pointing vector. It's a great question. We should work it out. I'll do so before next time. You do it too, and we'll see if we agree. Faikal also asks whether temporal gauge is the same as Coulomb gauge. And no, that's not quite true. Coulomb gauge is the gauge in which, in the vector field way of saying things, the divergence of A equals 0. Here we're not working with the spatial components of A, we're working with the temporal component of A. So time gauge is a little bit different from Coulomb gauge. I was mostly just wanting to illustrate one choice of gauge, but it's quite interesting to work through these things with other choices, and you should also look at Coulomb gauge. Armin asks, is a space-time split necessary, or is it also doable without it? And it's a good question, Armin. So the spin foam formalism is the attempt to do loop quantum gravity without a space-time split. So it does a path integral approach to this quantization. And as you know, in the path integral, we tend to keep covariance. So you work with the path integral e to the I action integral, and there we have space-time covariance nicely explicit. That can be harder to show other things in the path integral formalism, things about unitarity and such. There are different advantages and disadvantages. In the case of loop quantum gravity, it was historically developed first in the Hamiltonian formalism, and I'm partly doing it following that historical development. But there's another reason I'm doing it this Hamiltonian way first, which is that it's easier to understand the basis states that we use in loop quantum gravity from the Hamiltonian perspective before you go into the path integral. But you could certainly do this differently, and other people have, where you just jump straight into the path integral spin foam formalism. Deepan asks, will there be any issues in Taylor expansion for obtaining local coordinates due to a Planck scale presence in GR? That's a wonderful question, Deepan. Very much going back to the last lecture where I was arguing we can't carry this stuff out to arbitrary spatial scales, space-time scales. So yes, I agree with you, but let's not confuse two issues. What we're doing right here is treating standard classical general relativity. And in classical general relativity, we're dealing with a continuum theory that has no Planck scale cutoff or anything like that. And what we're doing is we're reformulating the variables of that theory in order that we could better understand quantization. And it may be that the result of that kind of quantization is to cut off the scale that we're working at. But it doesn't mean that we can't do that as a classical theory. So here we don't have to worry about that. We're just trying to recast general relativity at the moment, and then maybe later we learn that there's a intricacy and subtlety at the end. All right. Mateus.
Would you like to take maybe Idris, who he's raising his hand?
Oh, please, I can't see the raised hands. Yeah. Why don't I do that, and then maybe I'll stop for today.
Yeah, sounds good.
Yeah, can you hear me?
Yes.
So yeah, thank you, Professor, for your lectures for today. I have a questions for your last discussions on tetrad formulations of gravity, because we know in standard general relativity, we usually using the symmetric type of metric. And in tetrad formulations, since we have mixed kind of index, does it mean that we have extra degree of freedom? And so how come we could arrive in the standard degree of freedom of GR? And the second question is, it's probably trivial, but because of the nature of the quadratic form of tetrad, when you express it in terms of metric, does it mean that we have the also like the freedom to choose directions in working with tetrad? Thank you.
Yes. Okay, so let me do the second question first. We definitely have freedom in the tetrad formalism about choice of directions. In fact, that is going to be our gauge freedom. So the way I was saying that is that we have this Lorentz transformation invariance of the local orthonormal frame. You can make a Lorentz transformation of your laboratory and you'll get another perfectly legitimate laboratory. And that's so that would be a boost maybe, or but you can also just do a rotation of your laboratory, and it's another legitimate laboratory you could set up. So this is the freedom that we have, and that's going to become the gauge freedom. It's going to be like the body axes, the different choices of body axes that we had in the cat. We're going to just freely change from one frame to another. So that's going to be the gauge freedom in this formulation. And Idris, I had your first question clearly in mind, and then I got distracted by the second question. Can you just say again one word to cue me on the first?
Yeah, I mean, like in the classical GR, we have the symmetric situations, but in here we have two index mixed up.
Yeah. So yeah, that's a perfect lead into next week. So thank you. Next week, we're going to try and study what connection, what gauge potential is associated with this formulation. And the reason I'm saving it for the third week instead of treating it now is that it's the most complicated part of this discussion. It involves some subtleties and understanding how we're using this gauge potential. And you're getting to one of those subtleties, which is that we're going to have to use what we call a spin connection. And we're, in fact, in order to get a canonically conjugate variable, we're even going to have to modify that spin connection. So, so you're exactly right. Although you were worried, for example, whether we're going to have more degrees of freedom than GR has at the end. And you can show that when you impose all the constraints, that doesn't happen. So defining the correct connection is subtle, but once you have it in hand, it is going to be perfectly equivalent with standard general relativity, including having the right 2 degrees of freedom of the metric at every point.
Thank you.
Wonderful. Thank you, everyone. And I look forward to next week.
All right, thank you, Hal. Yes, as you said, the next lecture will take place next Wednesday at the same time, and we hope to see many of you there. See you.
Thank you, Johanna.
Bye-bye.
Thank you.